starting the computer. Okay, so just to give a very brief introduction, Professor David Wu from the University of Texas came today to guide us a bit through his work, or his several works on the PIR field, kind of to give us an introduction and a sense of all of the different, or some of the different flavors of PIR and for what PIR can be useful. So thank you very much, David, for coming today and joining. Mainly just one thing before starting, do you prefer to get interrupted with questions, or do you prefer to give questions at the end?
Please interrupt. I'd be happy to discuss that during the talk itself.
So thank you very much. The floor is yours.
All right, great. Thanks a lot, Carlos, for the introduction, and thanks for inviting me to speak. So I'm very happy to tell you about some of our recent work on private information retrieval, or PIR. And this is based on joint work with my students and collaborators, Alex Burton and Samir Menon. So let me sort of set the stage for what the primitive that we're interested in is. So this talk will be about something called private information retrieval, or PIR, or PIR. I'll sort of use these terms interchangeably throughout this talk. But the setting is as follows. It's a two-party protocol where we have a client, and then we have a server. And the server holds a database. So the database contains, let's say, records R1 up to Rn. And the client is interested in a particular record I. And the goal of a PIR protocol is for the client to retrieve the ith record from the database. So at the end of the protocol, the client learns the ith record. The privacy requirement for PIR is the server, or the database here, should not learn anything about which record the client is interested in. So at the end of the protocol, the server has no idea which query, which record the client requested. And so if this is the objective, it's actually very easy to satisfy. We can just have the client simply download the entire database. So this is what we call a trivial PIR scheme, where the client simply downloads the database, and now it knows all the records, in particular record number I. So I think it's important here to note that we do not require privacy for the database itself. The database contents is usually assumed to be public. The client is trying to privately retrieve a record from this public database. If you want privacy also for the server's data, then there are other protocols like oblivious transfer that ensures that. But that's outside the scope of this particular talk. So having defined a trivial PIR construction, that's not very satisfying because for many practical applications where PIR might be considered, which I'll describe a little bit on the next slide, it is infeasible for the client to always download the entire database, right? The database could be several gigabytes, terabytes long, big. And so it is unrealistic to expect that the client can just download everything. So for PIR to be interesting, we also impose an efficiency requirement, which essentially says that the communication should be sublinear in the size of the database. Ideally, the communication should even just be polylogarithmic in the number of records in the database. So you can think about it as if we did not require privacy, then all the client would have to communicate to the server would be the index I, and it would just retrieve the record I from the server and nothing more. And essentially what we want in PIR is that we want to do this in a privacy-preserving manner, but with similar kinds of efficiency from the client's perspective. The client does not have to fetch or download many bits of the database in order to reconstruct its record. So PIR in recent years has become sort of a major tool or major building block in a large number of privacy-preserving protocols. So I've just listed a couple on this slide, but there are many, many more. So a couple applications that might be of recent interest is Apple, for instance, has released an SDK for supporting private information retrieval and homomorphic encryption. Primarily for their application, they're looking at doing some kind of private voice call, caller ID type of application. So it's like your phone has received an incoming call. You want to check whether this caller or this number is known to be spam or not. So the idea there is that there will be some database of known spam calls, spam numbers. And basically, the phone, when it receives an incoming call, will query the database to learn whether the incoming number is actually in this list of spam callers or not. And of course, you want to hide who is calling you. That's a potentially very sensitive information. So private information retrieval is used to facilitate this kind of application. There's also been proposals of using PIR to do things like certificate transparency auditing. So if you want to check whether a certificate that you received is deposited in a certificate transparency log, you want to do that without revealing, let's say, your browsing habits to the server. One of the proposals for that is to use private information retrieval. So this is an application where we have some existing browsers. So for instance, Chrome has deployed some mechanisms to perform this kind of auditing with weaker types of anonymity guarantees. So something called k-anonymity. One of the proposals is that maybe using private information retrieval, we can get much stronger cryptographic guarantees. And anyhow, so this is hopefully just gives you a snapshot of the kinds of applications that people have considered for private information retrieval. And from my view, it's one of the simplest building blocks or simplest privacy-preserving protocols. So oftentimes, if you have a particular application where you demand privacy for one or both parties, private information retrieval can be something that fits in or plays a role in enabling those kinds of guarantees. Okay, so when we look at private information retrieval, and this is going to be the focus of this talk, there's several ways that we're going to measure efficiency, or there are several quantities that we care about. So as I mentioned, this is a client and server protocol, and I'm mostly going to be focused on two message protocols. So the client sends a query to the server sends back a response. So what are the efficiency metrics that we care about? Well, one is the size of the query, right? How many bits does the client have to upload in order to retrieve a record in a database? So that's the first metric. The second is how fast can the server respond to the query? And usually, the way that I'm going to measure this in this talk will be by a metric called the server throughput. So in particular, this is the ratio of the database size divided by how much time it takes for the server to respond to the query. And the reason that this is a useful metric or a relevant metric is that in a model without pre-processing, the server actually has to do a linear scan over every single record in the database in order to answer the query. And the reason for this is because of the privacy requirement, right? Because if the server does not know which record the client is interested in, it basically has to look at every single record. If there's one record in a database that the server does not look at, well, that means that the client could not have asked for that record, and that immediately compromises privacy. So this is why when we look at server throughput, it's really the time it takes to do a linear scan over the database size, and the question is, how long does it take to perform that linear scan? I will preface here that there is some recent work that actually shows how to get around this sort of linear scan barrier, where with some pre-processing, so there's some encoding of the database that the server develops ahead of time that is then used to reduce the online computation time. So there is a way to do that, but for the purposes of this talk, I'm only going to focus on constructions where the server has to do a linear scan. And for the most part today, all of the efficient constructions of private information retrieval that could potentially be deployed, they all work in this particular model. There are some exceptions, which I'll mention at the very end of this talk, but for the most part, this is sort of the state of the art in concretely efficient private information retrieval. From a theoretical perspective, we can do better. But the constructions from the theoretical world are not efficient actually to run in practice. And next, the metric, one of the more important metrics is something I'll call a rate, which is the size of the response as a function, the ratio of the record size to the size of the response. So this basically measures the communication overhead in the response. So how many bits does the client have to download to get a particular record? And essentially, we want the rate to be as close to 1 as possible, right? If the rate was 1, that means that if the client wants to get 1 bit of record, then it only needs to download 1 bit of information. Now, it could be the case that the client wants to retrieve 1 bit, and it needs to download 1,000,000 bits, right? It needs to download, or even a megabyte or something like that. Then the rate would be much smaller. So that would be like 1 over 1,000,000 if it's downloading 1,000,000 bits. So if we want a protocol to be high rate, that means that the communication overhead is minimized. And finally, for the constructions that I'm going to be describing in this talk, I'm also going to allow the client to upload a set of public parameters to the server. So there's an initial communication of some public parameters. This is a reusable set of public parameters that the server will use to process the query. You can think about the public parameters as a public key. So essentially at the beginning of the protocol, the client generates a public key and sends it to the server. And thereafter, the same public key can be reused for many queries. So the reason that we decouple the public parameter size from the query size is because the public parameters only have to be transmitted once. So if the client is making many queries, let's say one query every day, it only has to send its public key once. So like when it logs into the system, it sends over the public key. And then thereafter, the server can just look up the public key. It does not have to be communicated with every single query. Okay, so this is sort of the metrics that I primarily care about. Does the notion make sense? Are there any questions right now?
It doesn't seem so in the chat neither.
Okay, sounds good. All right, so let me say a little bit about what does the landscape of PIR look like. So it turns out that over the last couple of years, there's been a lot of work on developing faster and more efficient private information retrieval constructions. And we made great strides into bringing private information retrieval to be more practical. So here I have a graph sort of showing the different trade-offs in designing single server PIR protocols. And basically, I'm plotting communication versus computation. These are the two main metrics that I described. So for communication here, I'm basically defining it to be the sum of the query size plus the response size. So how many bits have to be uploaded/downloaded to perform a query. And then the throughput is basically how fast can the server process the database or process a query. And for comparison purposes, I'm focusing on the case of retrieving a 256-byte record from a database with 1 million records. And I'll show more benchmarks for other settings later on, but this is one particular case that may be of interest. This is actually a very small database. If you think about it, it's 256 megabytes. But I think it's still a relevant one to sort of show the different trade-offs for the different constructions. So basically, you want constructions towards the top of the graph and towards the right of the graph. So to the right of the graph, that means server throughput is very high and communication is very low. Towards the bottom of this graph, that means we have high communication and low throughput, so that's a negative. So you want things to be towards the upper right corner of this graph. So first we have a bunch of schemes where that's into sort of this client pre-processing model, where the client has to upload a public key before performing a query, and then thereafter the server responds. The nice thing about this model is that we can actually get very small communication. So if you look at it, we have some earlier schemes, so COPIR and FastPIR. So this is roughly pre-2018 or so. So this is maybe 5 or 6 years old. And then we have much more recent constructions like OnionPIR, Spiral, and Respire that get much lower communication. So for instance, Respire, if you want to retrieve a 256-byte record, the communication is something like 4 or 5 kilobytes, or maybe 6 kilobytes. So it's not that much bigger than the record you're interested in. Versus for previous constructions, maybe there's more overhead, so something like a few hundred kilobytes. So we made great strides in reducing the communication cost for private information retrieval. The throughput tends to be still on the lowish side, so something like processing a database at 200 to 300 megabytes per second for a single processor. So for large databases, this is still going to struggle. But there's been other works recently that's trying to make improvements on the throughput angle. So for instance, the simple PIR protocol is this extremely fast PIR protocol. It basically processes the database at roughly 10 gigabytes per second. This is essentially the memory bandwidth of the system. So the speed at which the server can respond to a client query is basically the same as the speed it takes to read the database from main memory. And this is sort of a bottleneck for any PIR protocol if you're doing a linear scan, right? Because you have to do a linear scan over the entire database. So the speed at which you can read in main memory will ultimately become a bottleneck for the system. Simple PIR basically achieves that memory throughput limit for single server PIR. So this is very nice, and the communication is actually not so bad. It's only about 100 kilobytes of communication to retrieve a record from the database. The drawback of simple PIR is that it's in a slightly different model, where instead of the client uploading a public key, it actually has to download a hint from the database first before it can process the queries. And in practice, this hint actually turns out to be very large. So the hint can be something like hundreds of megabytes for a reasonably sized database. So potentially, if you're using simple PIR, you'll need a way to download this. You have to make a large communication up front. And moreover, you'll need to store this hint if you want to make repeated queries. So this can introduce additional burdens on the client side. But in terms of throughput and in terms of online communication, this is a very lightweight, very simple protocol and very useful for many applications. Right. So the natural question then is, well, what if I don't want this hint, right? I don't want this initial high download. Is there anything that we can do? And so there's actually a more recent line of work. So hintless PIR and my own work with Samir on YPIR, which basically shows how to remove the hint from a simple PIR-like system at modest overhead. So the nice thing about these two constructions here, these two very recent constructions from late 2024, so this is maybe 6 months old at this point. These constructions there are no public parameters, then there's no hints. This is what we call a silent communication or silent setup model, where it's basically the PIR protocol is exactly a two-shot protocol. Client shows up, sends the query, gets back a response. No setup whatsoever. So no hint upload, no downloading a hint, right? So this is a very appealing, especially from a practical perspective. There's no authentication or anything needed. Just send the query, get the response. Two-shot protocol. And in terms of the throughput, it's not as fast as simple PIR. But I will preface here that as the database gets bigger, the performance basically gets to memory bandwidth. So there's some fixed costs of the protocol. So for a small database like 256 megabytes, we can only process, let's say, 2 gigabytes per second with YPIR. But if your database is, let's say, 16 gigabytes or 32 gigabytes, already YPIR is about 95% of the throughput of simple PIR. So the throughput of YPIR actually approaches the memory bandwidth of the system because the fixed cost for the overhead does not depend on the database size. So there's a fixed cost that you pay that does not scale with the size of the database. So as database size gets bigger, the cost of the linear scan actually becomes the dominant factor. And so you basically approach the memory bandwidth limit. And in terms of communication, it's going to be something like about 3 megabytes of communication for this particular case. So again, modestly higher than simple PIR, but has high throughput and doesn't require any of these hints. So this is roughly what the state of the art is. As you can see, there's not really a one-size-fits-all solution, right? There's no point like on the upper right corner of the graph here. We have points that are towards the upper half of the graph, but they're on the left half of the throughput side, versus we have things in sort of this quadrant here, which is high throughput, but high communication. So currently, we don't have anything that sort of has high throughput and low communication. And that's a fascinating open question and something that we are still thinking about here. But that's sort of what the trade-off looks like for modern PIR protocols.
David, sorry, one question. I have, two questions indeed. So the first one is, what about schemes like Newton PIR, which also show some, let's say, good trade-offs in performance results? Like, are not noted here because like it would be like just too many dots at the end if you put them all, or you didn't add it.
This particular construction, I guess. Do you know what it's based on?
I think it directly goes against simple PIR if I recall correctly, but I can say off the top of my head now. I think it builds on the top of simple PIR, and yeah, I don't know. I could lie, so don't quote me on that.
Fine. My understanding is that sort of the extreme ends of this graph, so in terms of throughput and communication, are basically reflective of the current state of the art. So I'm not aware of any protocol that's faster than simple PIR. Maybe you can get a little bit more communication out of it, but I think not by a significant margin. So I think as far as my understanding is, as of, let's say, 2 or 3 months ago, the schemes represented here represent the current state of the art in single server PIR. Yeah, so there are many constructions that I'm not listed here, and usually I did not list them because they are not competitive or they don't dominate the schemes that are already shown in the graph.
Yeah. Okay, that makes sense. And The second question that I had is mostly regarding the online communication cost that most of these protocols incur on. It's not a communication overhead that seems like prohibitively expensive, let's say, especially if it's a fixed costs independently of the size of the thing that you are querying, right? So do you think it's like it has that much relevance at this point, the online communication that the protocols incur on, if we are already at, like, let's say, kilobytes? Because kilobytes, of course, it takes some seconds to download kilobytes, but it's a size that it's acceptable enough, I would say, if you want to pay on that for privacy or for extra privacy. It's not like prohibitively expensive. So what's your take on that?
Well, I think it depends on the application. So for instance, if you're, let's say, doing certificate transparency auditing, and you're doing that on a per connection basis, or you're doing that very often, then the communication can add up, right? Imagine that if every TLS connection, you're going to make a PIR query, that's probably not tens of kilobytes for every single TLS connection you make. That's a lot. That adds up very quickly. Now, granted, if you're doing certificate transparency auditing, you're probably not going to be auditing every single TLS connection you make. You're probably going to be batching these queries at the end of a week or at the end of a session, in which case maybe you're only making a small number of queries periodically. In that case, a modest communication overhead, like tens of kilobytes, even a couple megabytes, is actually very reasonable. So I think it really depends on the application. What kind of frequency are the clients actually going to make queries, and what kind of bandwidth is available to sort of service those queries. So yeah, I absolutely agree that once we're in the regime of tens of kilobytes, hundreds of kilobytes, we can actually process these queries pretty regularly. So the communication overhead does not become super significant. I will say that as the database size gets bigger, as the size of the records vary, the parameters will start changing. So there will be some dependence on the size of the database. Again, it really comes down to the application. What do you say is the maximum communication that you're willing to tolerate for let's say, a single query? And then depending on that bound, different constructions might have different advantages and disadvantages. So I think, again, it really depends on the kinds of application you're looking at, what makes the most sense. But for many applications, I think the communication is already good enough. There is the caveat of, you do need these public parameters, and public parameters are not on the order of kilobytes right now. So they're on the order of megabytes to hundreds of megabytes. So those are more substantial. But if they can be cached or stored, then that could be less of a concern.
Fair point. Thank you.
Yep. Okay, cool. So what I'll try to tell you today is that I'll give you a flavor for how some of these communication efficient PIR protocols work. So I'll focus mostly on Spiral, and then the Respire protocol is sort of an improvement on top of Spiral for a particular parameter regime. So to give you a sense for how these PIR protocols operate, I'm going to describe the basic blueprint by Kushilevitz-Ostrowski of constructing private information retrieval from a homomorphic encryption scheme. So the idea here is I'm going to take my database, and I'm going to start by arranging it as a square, right? So let's say n is the number of records in a database. I'm going to rearrange it as a square that's square root n by square root n. Okay, so I've just put my database into a square. And suppose I'm interested in one particular record in this database. I'm interested in record in row 3, column 2. So the way the protocol works is as follows. I'm going to start by encrypting an indicator vector, indicating which row my record lives in. And in this particular case, my record lives in row 3. So I'm going to encrypt a 1 in row 3, and I'm going to encrypt a 0 in all of the other rows. So I want to indicate which row I'm interested in, and I'm just going to encrypt an indicator vector accordingly. And essentially, what a homomorphic encryption allows you to do is it allows you to perform computation on the ciphertext themselves. So for instance, given an encryption of 1 and an encryption of 2, I can take those two encryptions and I can actually homomorphically add them together to get an encryption of the result. So in this case, 1 plus 2, so I would get an encryption of 3. So here, what I'm going to do is I'm going to take the encryption of my query, and I'm just going to multiply it by each component in my database. So basically, I'm going to take 0 I'm going to multiply by each of the records. So again, that will give me 0. I'm going to take the second row. I'll multiply each record by 0. Take the third row. Each record gets multiplied by 1. Take the fourth row. Each record gets multiplied by 0. So the server doesn't have any idea what's happening here, right? The server only sees the ciphertext, but it can perform these homomorphic computations. And notice that if I perform this computation where I take the first row multiplied by the first ciphertext, second row multiplied by the second ciphertext, third row multiplied by the third ciphertext, and so on, and then add them together, because there's only a 1 in one particular row, what I end up with is exactly the row of the database I'm interested in. So I get a row of the database, and then I send it back to the client. The client decrypts and learns the element that they're interested in. They learn some other elements, but we don't care. Okay, so this is the basic blueprint. It goes all the way back to 97. And this is the blueprint that has been very successful in constructing private information retrieval using a homomorphic encryption scheme. And so here, because the database is actually available in the clear, we only need additive homomorphism. So we actually don't need things like fully homomorphic encryption. Okay, so once we do this, we send back the response, client decrypts. So notice that the total communication in this protocol is an encrypted query, which has size that scales with the square root of the database size. Yeah, question?
I think someone was unmuted or something.
I see. Okay, yeah, feel free to
indeed, I have one indeed. Could you elaborate a bit more on why FHE is not needed in this case? Maybe to give a bit more context. So you said the database is open in the clear, let's say, therefore fully homomorphic encryption is not needed.
Right.
That's assuming basically that the database that the user wants to query doesn't have any private information that the owner of the database doesn't want to leak.
Yes.
Okay.
That's right. Yep. So, and in fact, if you want to hide the contents of the database, using fully homomorphic encryption does not help you. Just because then you have to ask under whose key is the database encrypted under. And it has to be encrypted under the client's key in order for it to be meaningful. But then it's not clear how the database gets encrypted under the client's key, right? So this is why additive homomorphic encryption is sufficient for this, because we're assuming that the database is all in the clear. So only the query is encrypted. So you just need to be able to add and multiply ciphertext by scalars. Okay, good. And then the response is just a single row of the database. This has size that grows with the square root of the database size. So the question then is, okay, well, square root is great, but what if we want to do better, right? Can we have better communication? Can we further reduce communication? And in practice, square root is oftentimes very good already. Like for 1 million records, like a megabyte, the square root of that is something on the order of kilobytes. But if the database is, let's say, 100 gigabytes, then the square root of that is 10 gigabytes, which is still a prohibitively large amount of communication. So can we do better than square root? And the answer is yes. So what we're going to do is, instead of viewing the database as a grid, right, as a root n by root n matrix, instead I'm going to view the database as a hypercube, right? It's going to have many, many dimensions. So here I've drawn a 3-dimensional figure. And essentially what you can think about it is, what are these query vectors doing? Well, this query vector here is selecting along one of the dimensions of my grid, right? It's selecting for which row the database lives in. So if I have a hypercube, you can think about it as, okay, what is my query going to do? It's going to select along the first dimension. So in the case of a 3-dimensional cube, it basically tells me which slice of the cube am I looking at. So here it says I'm looking at slice number 3 of the cube. So I do the same thing I did before, and I basically project, using my query, onto the third layer of the cube. And now notice that we have a new database, right? It's a database, now it's a grid. And what do I want to do? I want to retrieve an element within this particular grid. So I can repeat the same protocol we had before. I can send you an encryption, which row the database, which row my record is within this cube. And then that will project it to a single row. And then I can say, okay, within this particular row, my record lives in the first column. And so now I get a projection again, I do multiplication, and suddenly I only end up with a record I'm interested in. So just by doing this, we can actually achieve communication that's cube root of n with a cube, and more generally, polylogarithmic in n if we have log n layers. So we have a hypercube of dimension log n. Now we can actually just project, and extract the element we're interested in. The caveat here is that we do now need homomorphic encryption, and the reason, or fully homomorphic encryption. The reason being that once I do my first layer processing, I take my database, which is in a clear, but after I process it, I now have an encrypted database, right? The server doesn't know where the element lives, and I want to project again. But now the setting is different. I have a database that happens to be encrypted. So in order to do the next layer of projection, sort of this inner product-like operation, now I need homomorphic multiplication. I need to multiply ciphertext together. So this is where fully homomorphic encryption comes into play. Okay, good. So this is the basic blueprint. This was known in '97. And in fact, you can actually already just take your favorite fully homomorphic encryption scheme and use it to implement this protocol. Turns out that the performance is actually really, really bad if you just do that, because fully homomorphic encryption is very expensive. So the server cost will be too big if you just do the naive construction. So the technique that we use in Spiral and sort of many subsequent works in this family, it does use fully homomorphic encryption, but it does so in a very particular way that gets us better concrete efficiency. And the key idea here is we're actually going to compose two different fully homomorphic encryption schemes. So it's going to follow a paradigm first introduced by Gentry and Halevi of building what's called compressible or high-rate fully homomorphic encryption. So let me give a little bit of background on how these schemes look like. So we're going to be using lattice-based cryptography. So lattice-based cryptography is the only mechanism essentially that we have of realizing fully homomorphic encryption. So that's what we're going to be using as the cryptographic building block in our scheme. And I'll give it a little bit more background on what these things look like. But the way that you can think about it is the ciphertext in a lattice-based scheme, they're basically noisy encodings of the message. And as you do homomorphic operations, the noise in the ciphertext increases. And if you have more noise, you need to have larger parameters to tolerate it, because if the noise becomes too big, you cannot decrypt anymore, right? If the noise is bigger than the signal, then all you have is noise, and that's not useful. So as you perform homomorphic operations on encrypted data, the noise accumulates, the parameters get larger, you get less efficiency. So most of the work in trying to use homomorphic encryption to do something useful is really a question about noise management. How can we make sure that the noise doesn't grow too big too quickly? Because if it does, then we're out of luck, right? Then we have to pay with a very high performance overhead. So what we're going to do in the construction of Spiral is we're going to consider two different homomorphic encryption schemes with two very different types of properties. So the first is Regev's encryption scheme. This actually goes all the way back to Regev's original work introducing the learning with errors problem. And Regev's encryption scheme has a very nice property in that the ciphertexts are small. So for instance, if I want to encrypt, let's say 18 kilobytes of message, I need a ciphertext that's only like 43 kilobytes. So only 2.4 times bigger than the size of the message. And as the message gets bigger, this actually gets better, right? If I want to encrypt 1 megabyte, my ciphertext has only 1.3 megabytes long, right? So this is nice if you're trying to build a PIR protocol that wants to support large records, right? Suppose the record is at least 18 kilobytes or 1 megabyte, and encryption of the record is not much bigger than the record itself. So that's good. So it's good for communication, it's compact. Unfortunately, though, Regev's encryption scheme does not support fully homomorphic encryption. It does not support homomorphic multiplication. The only thing it can do is homomorphic addition. So it seems like if we use Regev's encryption scheme, we would be stuck with the square root construction. We wouldn't be able to get better than square root n communication. So we cannot do multiplication. That's the drawback. The second scheme I'm going to talk about is the Gentry's to high waters encryption scheme, so the GSW encryption scheme. This is a fully homomorphic encryption scheme, so it's a very sophisticated. Its construction has a lot of capabilities. And so it supports homomorphic multiplication. And moreover, the amount of noise that's introduced in the homomorphic multiplication scales additively with the number of multiplications, right? So most homomorphic encryption, the amount of noise that's accumulated scales exponentially with the depth of the computation. Here, it only scales multiplicatively. Every time I multiply, I get an additive amount of noise added to my ciphertext, not a multiplicative amount. So this has very good noise growth. The way that it achieves this, though, is it has gigantic ciphertexts. You have to have very big ciphertext in order to support homomorphic multiplication and have very good noise growth. So just to give you a sense for how bad it is, if I want to encrypt 1 bit of data, I need a ciphertext that's almost 20 times larger, or sorry, 2 million times larger, right? It goes from 1 bit to 2.5 megabytes. So this is an extremely large ciphertext expansion. And you can imagine if I have to encrypt a database using the GSW encryption scheme, that's a 1,000,000x overhead. So a gigabyte becomes 1,000 terabytes, right? This is something that's not going to be practical, but it has very good homomorphic multiplication. So the question is, okay, yeah.
Well, sorry, David, one question. In here, is there any particular reason why people avoid using other FHE schemes, like, I don't know, TFHE or whatever, anything? And basically they do bootstrapping to reduce the noise
so
increase?
not good, at least for the PIR application. If you just use off-the-shelf FHE schemes, let's say you're just using TFHE to implement things, it will be significantly slower.
Like query-wise or encryption of the database-wise?
So the encryption of the database will be much slower, and processing the query will be much slower.
Okay, so both. Okay, I see.
Yeah. I think I would guess that the overhead would be at least 1,000x.
Oh, wow. Okay. Okay, I didn't thought it was going to be that bad. Okay, thank you.
Right. So in fact, a lot of works that have tried to use fully homomorphic encryption, they basically don't try to use homomorphic multiplication at all. They actually use other mechanisms to avoid using homomorphic multiplication just because the overhead is so high.
Because there have been some recent improvements on bootstrapping efficiency, meaning some for example, are going back to circuit bootstrapping and basically try to enable a parallelization of all of them. There's also amortization of bootstrapping where you pay for one, but you execute all of them. The constants are massive, of course, but there's maybe some hopes. Do you think if the situation gets better, then it would make sense to go for this homomorphic multiplication, and it still will not be the case?
I don't think so. I think for PIR, because the type of computation is so much simpler than general computation, you actually don't need very sophisticated homomorphic multiplication. There are actually always going to be better lattice techniques that do better. So homomorphic encryption, the reason that it's slower is because it's more general. It can do a lot more than the kinds of things that we're going to need for PIR. So the PIR application, I view it as we want to do homomorphic encryption for a very, very simple computation, basically computing linear functions almost, computing inner products, matrix vector products. And for this, if you try to design a tailored scheme, you can actually do much, much better. So that's sort of what all of the recent line of works have done to actually make PIR practical at scale. Using tailored homomorphic encryption schemes can give you significant improvements in terms of concrete efficiency.
Thank you.
Yep. So the main question in Spiral is, can we get the best of both worlds? So we have these two schemes, one that's fully homomorphic, one that's only additively homomorphic but has small ciphertext. Can we do both? And that's exactly what the underlying design principle for Spiral is. We're basically going to use the GSW, this nice homomorphic encryption scheme, to perform homomorphic multiplication, but we never want to communicate GSW ciphertext because they're so big. So we're going to use regev encryption scheme for all of the communication. So let me just give you a sense for what that looks like. So I'll start by talking about regev's encryption scheme. So in regev's encryption scheme, I have a message, I have a secret key, and I have the ciphertext. And the invariant that you should think about is if I multiply the secret key by the ciphertext, so the secret key is a vector, ciphertext is a vector, I multiply them together, I get the message. Yeah. And technically everything is working over polynomials, but that detail will not be relevant for this talk. So essentially, if you have the secret key and you have the ciphertext, you get a noisy version of the original message, right? You just multiply them together, you get the message. And to support decryption, basically we just scale up this message. So we have to somehow get rid of the noise. So all we do is we just scale up the message by a large constant, And we say that as long as the noise that's added is much smaller than a scaling factor, or sort of the size of each region, then we will be able to decrypt. So we have recovered a noisy version, and then we round to the nearest multiple of the scaling factor, and that's it. Okay. So if you think about this type of encryption scheme, the rate, or so how big is the ciphertext relative to how big the plaintext is, this is basically saying that the plaintext is a log p bits, so it's an element of ZP, so an integer mod p, and the ciphertext is 2 elements mod q. And q is usually something like twice the size of p in terms of the number of bits. So you can get something like the overhead or the expansion factor is something like a quarter. So the onion PIR scheme, in fact, uses this exact encoding scheme, and basically the ciphertext expansion is a factor of 4. Okay, turns out that you can actually do better. Instead of encrypting 1 bit at a time, you can actually encrypt an entire matrix at a time. And the reason that this is better is because you can actually reuse the randomness that you're using to encrypt each component of the matrix. This actually does not compromise security. And so this can actually reduces the size of the ciphertext. So essentially, instead of having the rate be 1 over 2 times log p over log q, now it becomes n squared over n squared plus n. I'm encrypting n squared things, but my ciphertext only needs n squared plus n number of things. So the extra factor of n here, this is just the randomness that's used to encrypt. So in particular, if you encrypt matrices at a time, you can pack more information into a single ciphertext with less overhead. So this will be useful. The second observation is that this is additively homomorphic, and this follows just by looking at the decoding invariant, right? So again, the ciphertext is an encryption of M. If I multiply by the secret key, I basically get M, right? S times C gives me the message. So if I have 2 ciphertexts, let's say C1 and C2, that encrypts M1 and M2, that means if I multiply them by S, I get, by the secret, I get the corresponding matrix. So you can observe that if you just add these 2 relations together, you get that C1 plus C2 is an encoding of M1 plus M2. So regevs gives you additive homomorphism for free. Okay, so the second encryption scheme that I mentioned is this encryption scheme of Gentry-Sahayan waters, or GSW. This is actually the same encryption scheme that's at the base of TFHE. So TFHE is actually based on the GSW encryption scheme. And in GSW, basically what happens is I now have a very redundant encoding of the message, right? So the invariant that I'm going to use is the following. C here is the ciphertext. S here is the secret key. If I multiply the secret key by the ciphertext, before, I just get the message. In GSW, I don't just get the message. I get the message times something. I get the message times the secret key times the gadget matrix. What is the gadget matrix? It is powers of 2 thing. So basically, it is the powers of 2 along a diagonal. Okay, so this is the gadget matrix. The construction will use more general versions of this, but again, I won't get into the details. Okay, and the way that you can, and the reason that we care about this gadget matrix is it has this nice binary decomposition like property where if I have a vector v, if I take its binary decomposition and I multiply by the gadget, I get back v again. So it's a way to take a dense vector and make it short. So that's the only property you'll need for this talk. Okay, and as you can probably see from the picture, the size of the ciphertext is significantly larger than the size of the message, right? The message here is a single bit. Mu is a single bit. And S and G are these gigantic matrices now, right? And if you want concrete parameters, basically to encrypt a single bit, you need a ciphertext whose size is D. So that's the size of each of these elements times n plus 1 squared. That's the size of the n plus 1 squared times log q. That's the number of entries within this ciphertext matrix, right? So concretely, you plug in these parameters, you get something that's pretty abysmal. Like the ciphertexts are very big. And the reason for that is because the ciphertext, you can view it as a very redundant encoding of the message that turns out to have very nice properties. So the nice property that we will be using, so this is the key algebraic step in this talk, is this very nice homomorphism between regev and GSW. And this was introduced in the context of TFHE. So this is actually one of the major innovations in the TFHE scheme is how do you do this sort of this multiplication between regef and GSW, this turns out to have very nice properties. And the idea is actually quite simple. If I have a regef ciphertext, I multiply by the secret key, I get the message. If I have a GSW ciphertext, I multiply by the secret key, and I get the message, but I multiply by the secret key, multiplied by the gadget matrix. So what you can do is the following. Suppose I take my GSW ciphertext, and I multiply by G inverse times the regef ciphertext. So G inverse makes this regef ciphertext into a binary thing. And now notice what happens. I take S times this GSW ciphertext. By the GSW invariant, that's just mu times S times G, right? So I get mu times S times G inverse of the regef ciphertext. G times G inverse just cancels out. So I get S times this regef ciphertext. But what is S times the regef ciphertext? That's regef decryption. That just gives me the message back. So notice that what we are able to do by taking the GSW ciphertext and multiplying it by the regef ciphertext, I actually get an encryption of mu times M. Okay, so now I've gone from a GSW ciphertext and a regef ciphertext back to a regef ciphertext that encodes the product of the two inputs. So we have basically done a homomorphic multiplication between a regef encryption and a GSW encryption. Okay, with the noise terms, this is what the relation looks like. This is actually not so important. I just want to show that for correctness, all we need is just multiply these together, and you get homomorphic multiplication. Okay, all right, good. So just to summarize, we have on the left, we have the regef encoding. On the right, we have this GSW encoding. And another way that you can think about the GSW encoding is, I said that S times C is mu times S times G. If you actually write out what that looks like, it basically looks something like this. You have one block of ciphertext, and then you have mu times I, 2 times mu times I, and so on and so forth. So it's a very redundant encoding of the message mu. The mu is encoded many, many times in the ciphertext. And the key property that we're using is that if you have a regef encoding of the message M and a GSW encoding of the scalar mu, you can get mu times M. Okay, so what does the Gentry-Halevi blueprint look like now? How are we going to use this to build private information retrieval? So the database, recall, is represented by a hypercube. So I'm going to say the first dimension of the hypercube is 2 to the new 1, and then all of the subsequent dimensions have dimension 2. Okay, so that's just the configuration of my hypercube. The way the query looks like, what the query looks like, is it's going to consist of many regef ciphertexts, basically encoding the indicator vector, so encoding which bit I'm looking for along the first dimension. So this is exactly the same thing I presented earlier with the grid, right? I have an indicator vector that shows which row I care about. Here I'm just saying which slice of the hypercube am I interested in. So that takes care of the first dimension. And for the subsequent dimensions, I'm just basically they're binary dimensions, right? So there's only 2 elements within each slot. I'm going to have a GSW ciphertext that indicates which index I'm looking at in those subsequent dimensions, and that's it. This is the construction, and the point is that I guess that doesn't matter. The point is that the response will just be a single matrix regef ciphertext, right? So I encrypt using regef the queries along the first dimension, and then I'm going to do a homomorphic multiplication with each of these GSW ciphertexts. And notice that the homomorphic multiplication has the property that it produces a regef ciphertext. So at the end of the day, I get a regef encryption. That's good because regef encryptions are compact, right? They're small. Okay, so what does the overall protocol now look like? I take my database, I use my regef encryption of the indicator vector along the first dimension to basically project onto the first dimension, right? So now I get a regef encoding of the database slice, and now I just use the GSW encodings to select for the subsequent components. So here I'm selecting for this row, oops, and then I'm selecting for this column, right? And at the end, I get a single regef ciphertext, and that's it. Okay, so does the overall protocol make sense? So it's using homomorphic multiplication, but the multiplication is done by using regef multiplied by GSW. Okay.
Yeah, it does make sense.
Okay. Excellent. Good. So at this point, you might say there's something that looks fishy about this picture. It looks like you're communicating GSW ciphertext, and I just spent a lot of time telling you that GSW ciphertexts are humongous, right? So doesn't that mean the queries are humongous? Turns out the answer is yes. In fact, each of these single bits, encrypting a single bit, is 4 megabytes for the concrete parameters we look at. So this is going to be a gigantic ciphertext. And in fact, if you plug in all of the parameters, the overall query size for the original Gentry-Halevi construction is something like 30 megabytes, which is, in the case of the size of the data, relative to the size of the database, might be like 10% of the database size. So this is a gigantic query in the grand scheme of things. Also note that there's a clever technique using polynomial encodings by Angel et al. That shows how to compress many regev encodings. So I'm not going to go into details of how that works. Basically, you can actually compress the regev encryptions, but the GSW ones, we don't have a mechanism yet. Okay. And if we compare against sort of prior PIR constructions based on just regev style encryption, there the queries were much smaller, something like 66 kilobytes, because they only needed to communicate regev ciphertext. They did not need GSW. So it seems like using GSW is great because you can do homomorphic multiplication, but the ciphertexts are so big that you don't gain anything in the process. So the key idea underlying that, by the way, how am I doing on time? I think I might be running just
we're 8 minutes away from like the formal time, but I mean, it doesn't. I don't think it matters. Like it's much more important that you can explain everything. Like if whoever needs to leave can leave.
Okay, sounds good. So I'll just keep going. But yeah, if I'm running short on time and you want to stop, just let me know and I can.
No worries. That's not the case. No worries at all.
Okay, great. Okay, good. So what we do in Spiral is we're going to expand. We're going to sort of show how to compress these very large GSW ciphertexts. We're going to compress them using regev encodings. And I should note that this was also done in a prior work by Muhershis et al. In the onion PIR construction. They considered this case for the for the scalar case. And in Spiral, we gave a more general toolkit for switching between regev and GSW. And it turns out that the transformations that we develop are both useful for query compression and for response packing. So I'm not going to go into the full algebraic details. I just want to give you a picture of sort of what's happening under the hood inside Spiral. So our goal is to somehow build a GSW ciphertext, right? So a GSW ciphertext is one with the following property. If I take the ciphertext and I multiply by the secret, I get basically the secret times this gadget times the message, right? So let's take a look at what my goal is. I'm trying to build mu times s times g. What does that look like? That looks like a C0, and then followed by many redundant encodings of the message. So basically, the message mu scaled by the powers of 2. Where does the power of 2 come from? Is basically this gadget term here. And what I want to do is I want to construct a ciphertext C such that when you multiply C by the secret key, you get this picture here. Okay, so that's my goal. So let's just first write down S times C. Yeah, S times C will look something like this. S times A and then S times B and so on. So the first observation is that if you look at what's going on with these blue and purple blocks, it's saying that I want to find a B0 such that when I multiply by the secret, I get the message, mu. I want to find a matrix B1 such that when I multiply by the secret, I get 2 times the message, 4 times the message, and so on. If you look at this picture, this looks like regev encryption, right? It's a matrix that when multiplied by the secret key gives me the message, right? So you can think about the GSW ciphertext as you have a header that's C0, and then a bunch of regev encryptions of the powers of 2 multiplied by the message. This is an equivalent way of thinking about GSW. Okay, so that's one thing. The second thing is we need that this S times A here to equal C0. I'm not going to go into details of how this works, but this uses somewhat standard key switching techniques from homomorphic encryption. So there's a way to construct a matrix A such that S times A is actually the first block of the GSW matrix. This is basically a key switching mechanism, but we can do it. So what this picture is showing is that essentially, I don't need all this full ciphertext. What I can do is I can just have many regev encryptions of each of these smaller components. But so far, it doesn't seem like we got anything because we have a lot of different regev encryptions. So it's like if I give you each of these components, that's no better than just giving you the GSW ciphertext. So the second idea then is the following. Let's take our query. The query has these regev ciphertexts and these GSW ciphertexts. The regev ciphertext, I said, we can pack using that already is small, right? So we don't do anything fancy here. And the GSW ciphertext, basically, it's just taking a message multiplied by many powers of 2, right? So what I can do is I can just have a bunch of regf ciphertexts that basically encode the powers of 2 times the message, right? And then from these regf ciphertexts, I can sort of recompose them together or sort of combine them together to actually get my GSW encoding. Okay, so suppose I can do that. So far it doesn't seem like we made any progress, right? We still have a large number of ciphertexts. Sure, we've taken the GSW ciphertext and broken it up into different pieces, but there's a lot of different pieces, right? So we don't have any compression yet. So the second step is that, the progress that we made is we went from these ciphertexts into exclusively regf ciphertexts. And I showed you, or I claimed before, that if I have many regf ciphertexts, we can actually pack them into a single regf ciphertext. So this is the technique by Angel et al. And further improved by Chen et al., where basically they show that if I'm encrypting many different scalars, so here I'm just encrypting many 0, 1 values, or 1 times powers of 2, I can actually pack many different scalars into the coefficients of a polynomial, and then just encrypt the entire polynomial at once, right? So instead of encrypting 1 bit or 1 scalar at a time, I can now encrypt a vector of bits at a time. And that's exactly what we do here. So we can pack all of these things together into a single ciphertext. So now we started with something very big. We have something much smaller now. And we can also use similar techniques to actually reduce the response size. So the same kinds of homomorphism and compression, we can actually use multiple ways. Okay, so to sort of summarize now, the overall Spiral protocol operates as follows. We have the public parameters. The public parameters are basically the public key. So it's the public key used for homomorphic evaluation, these key switching matrices, these ciphertext expansion and translation matrices. All of these are basically key switching matrices from the homomorphic encryption world. These are the public parameters for the scheme. The query consists of a single regf encryption. So I just send you a regf ciphertext to the server. And what the server is going to do is it's going to use the aforementioned homomorphic expansion procedure that I just described to actually produce these large queries, right? These regf ciphertexts, these GSW ciphertexts. And then I just use the protocol I described before. I project along the first dimension, then I use the GSW to sort of select along the subsequent dimensions. And then now I have a final regf ciphertext. We can use sort of the same, sort of the inverse process of the expansion to compress into a single short ciphertext. And this gives us a communication efficient construction. So just to give you a sense for whether this works in practice or not, here I'm comparing against some earlier schemes. So Spiral is about 2 years old now. So I'm only looking at schemes from over 2 years ago now. So these are older constructions. I'll talk more about newer constructions at the very end of this talk. So here I'm looking at a configuration where we have 8 gigabyte database. So each record is something like 30 kilobytes, and there's about 250,000 records in the database. So sort of compared to the previous state of the art, we get improvements in both the communication and the computation simultaneously. So we almost double the throughput, and we reduce the query size and response size by over a factor of 2. The drawback or the limitation of Spiral, where we pay, is the public parameters are larger because we have larger key switching components. But again, this is a one-time setup cost, right? Like if you have an application where you're making many queries over a period of time, you generate your public key once, and then that's good enough for all future use. Okay, so I'm currently not comparing against some of the later constructions like PHOTO-PIR, Simple-PIR, Piano, and so forth. I'll mention those at the very end of this talk.
One quick question also in that regard. So obviously, I mean, there's the communication overhead is definitely much smaller, yet still you need to, let's say, send some stuff. Could you benefit from the fact of not needing TLS or basically any kind of encryption through the wire anymore? Meaning your queries are already encrypted, let's say. So
right.
It's not that you really care. I mean, you can care in other regards, but as for leaking private information, let's say, about your query, you don't need TLS for that.
Sure. That's a good point. Yeah, so we don't rely on TLS for any privacy guarantee anymore. I think,
Okay,
though, that since the overhead of TLS is so small, I don't think that makes
fair
a
enough.
significant in the bottom line. Yeah,
Hmm.
but certainly, for the protocol, we don't need to assume a secure channel anymore. All the
Okay,
VAs are. Yep, that's a good
makes
point.
sense.
Mhm. Okay, and if you want to sort of get a sense for the scaling, here we have a throughput for different database sizes. So as a function of the number of the size of the database in terms of the number of records and how long it takes for the server to respond to a particular query. So you can see that the Spiral protocol, so the one shown in blue here, we can get something like 300 megabytes per second on a single thread, single core processing. So again, if you have multiple cores, all of these things are very parallelizable. It's just really just doing a linear scan over the database. You can get much faster performance that way. I'll mention a few optimizations that might be relevant. So this is for the large record setting. I'll talk about the small record setting in a little bit as well. So the large record setting is oftentimes what I call a streaming setting, where the same query is used to retrieve a very large record in the database or used to retrieve records from multiple databases. So the same query used on multiple databases. This is a setting that's suitable for things like a private video stream, where the ith copy of the database contains the ith block of the media content. So imagine you're trying to do a private Netflix, right? You want to stream a movie without revealing which movie you're interested in. So your query will be the movie index, and then you would basically just be reading it over the duration of the movie. It's also useful for things like private communication, so private voice calls. So if you want to do a voice call using PIR, basically the database would be the voice stream, and you would just be repeatedly polling the same mailbox to get the latest content. So this is the setting where PIR is used in a streaming fashion to retrieve data. And then oftentimes the goal here is to minimize the online costs of the protocol. And the nice thing here is that any fixed cost, like public parameters or large queries, they can be amortized over the lifetime of the stream. So imagine that I'm trying to retrieve a 2 gigabyte record, so let's say a movie, from a database. That can happen over a period of time. And the initial query and the large public parameters, those will essentially be a small part of the overall cost of actually downloading the record itself, right? So in this setting, we can have some different optimizations. So for instance, we can remove some of these compression techniques. This allows us to get smaller noise growth in the underlying homomorphic encryption and get better performance. So for instance, here we can drop some of our query compression techniques altogether and just send a big query in a clear. Sure, the query is 30 megabytes, but if you're downloading 2 gigabytes of media, the initial 30 megabytes of communication may not be such a big problem anymore. So now we really care about throughput. And it turns out that once you do this, you indeed can get much higher throughput. So the purple lines here basically show the version of Spiral for the streaming setting, where we don't do query compression anymore. We just send a big query over, and then we just have the server respond. Notice that the throughput can be something like 4x to 6x higher. So we can get throughput on the order of like, I think 1.5 gigabytes per second to something like 2 gigabytes per second. Right, so we peak at something like 1.9 gigabytes per second. This is over 12x faster than any previous PIR construction. So again, it shows that using these lightweight holomorphic operations, this regv and GSW, is great for throughput on the server side. You come at the cost of communication, but if you don't care so much about this compression or compressing the upload, now suddenly you can get much better performance.
One question, David, in regards of that. So do you think, how can I frame this? So let's say I basically do, like I'm doing this query, right? Are we assuming that the server is using all threads and basically all its computational resources in order to give me this throughput? Meaning, can a single server serve content for n people at the same time without it affecting significantly the throughput? Do you see where I'm going?
That's a great question. Yes, so this is actually something that we investigate in the context of YPIR. So we developed this notion. So currently, everything I'm describing is single client, and then the server is using a single thread to process the query. So certainly you can use multiple threads. That will give you a modest improvement to the throughput. There's a limit to how fast you can go because ultimately it'll be bottlenecked by how fast you can read main memory. So that will be the ultimate bottleneck. So with multiple threads, that doesn't help you there. But then the question is, what if I have 1,000 clients all coming at once making queries? Do I have to do a linear scan for all 1,000 of these clients, one after the other? That would be very burdensome for the server. So one of the things we do in YPIR is we actually do this something called cross-client batching. So the idea here is that I have a batch of clients, all independent, so they're not communicating, they're not coordinating. They all send their queries at once. And basically what we show is that the server can actually use a single linear scan over to the database to actually process all of the queries at once. So you don't have to do, like if you have K clients, you don't have to do K independent linear scans. You can sort of amortize the cost of the linear scans and process all K queries at once. So that's a way that you can get effective, much higher effective throughput. So basically let's say the amortized throughput can actually be higher than the memory bandwidth of the system because I'm taking a single linear scan and using it to respond to 4 or 10 or 100 queries at once. So yes, this is something that we can do. And I think for practical purposes, this is essential because oftentimes the server will be servicing many different queries simultaneously. And we don't want to have to basically pay the full cost of a linear scan for every single one of those queries. So yes, we can do it. And different constructions will have different trade-offs for that. But generally speaking, in YPIR, we show that this optimization applies for most of the existing PIR schemes out there. So you can do this kind of thing.
Makes sense. Thank you.
Yep. Okay, good. So just to give you a sense, for the fastest version of this Spiral, it gets a throughput of something like 2 gigabytes per second. The rate is actually very good, so 0.8. So this means that the inverse of this is a 1.25. So you only pay a 1.25x increase in communication, right? So if I want to fetch 1 gigabyte of data, I only have to download 1.25 gigabytes of information. So the overhead in terms of communication over direct retrieval is actually quite small. So that's one appealing aspect of this construction. But of course, we pay for it with very large public parameters and very large queries. So this is really only meaningful in a streaming setting where you're really downloading large payloads from the server. For small records, you never want to do this. But for large records, this is very, very interesting. Right, and in fact, if you model AWS compute costs as one metric for how expensive something is, the cost of privately streaming a 2 gigabyte movie from a database with something like what is 2 to the 14? It's something like 16,000 movies. This is roughly only about 2x more expensive than directly downloading from AWS. Now, this is a little bit misleading because you would never use AWS to actually serve a movie. But if you do that, the cost of this protocol in AWS compute and communication costs is only a factor of 2 over the no privacy baseline. Of course, if you serve a movie over a CDN, where the cost of communication is much lower, then there'll be a bigger gap, but I don't have the numbers for how expensive it is to serve a movie over a CDN. So this is just give you some perspective on how this translates to monetary costs. Okay, good. So I'm mostly done describing Spiral. So basically, it develops new techniques to translate between these FHE schemes, and they give us a new way to explore communication computation trade-offs in single server PIR. And the techniques that I described here, sort of this translation between regev and GSW, this is used for both query compression and response compression in our final protocol. We also have some automatic parameter selection, which I think is very useful in a setting of any kind of lattice-based system. So with lattice-based cryptography, there's always a lot of parameters that you have to pick. And the parameters basically dictate the overall performance of the construction. With Spiral, we actually have a systematic way of going about this, where you just tell me the size of the database, so number of records, size of each record, and it automatically figures out what lattice parameters to use to basically optimize it for your requirements. Just to summarize, these are the sort of the base versions and the streaming versions of Spiral relative to prior work. So in the time I have left, which maybe in another 10 minutes or so, I'm going to tell you a little bit about how we handle small records. So this is a more recent improvement on Spiral called the Respire system. So before, Spiral, I said, was optimized for the very big records. That's the streaming setting. It was okay for moderate size records, like tens of kilobytes. But what if the records are very small? What if I want to retrieve, let's say, a 256 byte record? So maybe like a DNS record, if you want to do like private DNS, usually those records are on the order of a few hundred bytes. Maybe you're trying to retrieve a SHA-256 hash. Then it might only be 32 bytes. So these are applications. Retrieving a hash value is useful for both the certificate transparency auditing. It's also useful for doing things like password breach monitoring. So if there's a password dump and you want to see if your password happens to be in this list of compromised passwords, usually you'll be looking up a hash of the password. So these are settings where the entries in the database are actually very, very small. And so the previous constructions where you are uploading like hundreds of megabytes of information for a single query or for a small number of queries, they don't really make good sense anymore. So the Respire protocol is a way to further optimize things. So let's first take a look at Spiral. So if this is the original example that I described, so with Spiral, if you have a database with, let's say, 1 million records, each 256 bytes, the size of the query and the size of the response are already on the order of kilobytes. And both the query and the response are significantly larger than the size of the record, right? So in absolute terms, this is not too bad. But if you're making these queries often, like let's say for private DNS, these queries might be happening quite often. You don't want to be paying these tens of kilobytes on every query, right? So the question is, can we do better? And the reason that things are big is that lattice ciphertexts are big, right? That's always has been the issue with lattice-based cryptography. Things are just big, right? The parameters are large, and it's very hard to get things to be compact, right? Lattice-based signatures are much bigger than, let's say, ECDSA signatures, again, because lattice parameters are big. And so the question is, okay, what can we do, right? There seems to be a fundamental limit. And in fact, if we look closer, it seems even more fundamental, because if we look at the query, it's a regf ciphertext, right? It's an LWE ciphertext, and an single LWE ciphertext is large, right? So if you just look at the parameters, the dimension of this vector is 2048, the modulus is 56 bits or 7 bytes. If I just give a single ciphertext, that's already 14 kilobytes. And it seems a little bit far-fetched that you have an encryption scheme. You're using an encryption scheme to build a PIR scheme. And yet, you don't even communicate a single ciphertext, right? Like a single ciphertext should be the lower bound in a communication. Like you can't do better than communicating a single ciphertext, because less than one ciphertext is 0 ciphertext, and you can't do anything with 0 ciphertext. So it's like, as soon as I communicate one ciphertext, I'm already doomed, right? I already incur 14 kilobytes of communication. So the question is, okay, so what do we do? Can we get small communication when the records are small? So it's also the case with the response size, right? The response is a ciphertext. I need something to be secure, right? The server shouldn't learn what it is. So it seems like both the size of the query and both the size of the response, the lower bound that we use a lattice-based construction is 14 kilobytes of query, 14 kilobytes of response. I need to communicate a single ciphertext. And if that's the metric, then Spiral is actually pretty good. It's pretty close to the limit already, right? Indeed, the Spiral, the query and the response each consists of a single ciphertext. So the somewhat surprising aspect is in our work on Respire is that we actually break both of these barriers. So the query size is only 4 kilobytes, response size is 2 kilobytes for this particular setting, and the throughput is the same. So we don't pay in throughput, but we get a substantial reduction in both the ciphertext size and the response size. And the question that you should ask then is, okay, this is a lattice-based construction, and I'm telling you that I have a construction where I'm not even communicating a single ciphertext anymore. So what in the world is going on here? Okay, so we get fairly substantial reductions. So the observation comes back to the query compression technique. So let's look at Spiral query compression. I basically take all of this gigantic query and sort of squish it down into this single regf encoding. That's what I do. And if we think about it, what is this regf encoding? Well, it's basically a representation of some vector, right? What is the vector? It's some kind of polynomial. So here I've shown the example. Suppose the polynomial was 1 plus x cubed. I basically take the coefficients and stick it into the coefficients of the polynomial. So constant term, linear term, cubic term, right? And let's say the degree of the polynomial, sort of the dimension of the vector, is 8. So when a database records are very small, and when a database is relatively small, the observation we have is that most of the coefficients in this polynomial are actually 0, right? I actually don't need to pack that much data into the polynomial itself. Like this D here, I don't get control over. This D is set by the security parameter. This is always 2048 or bigger. So that means that I can always encrypt 2000 things. But if I only care about 5 things, I'm using 2000 slots to encrypt a very small number of values. So there's a lot of waste. So can we exploit that somehow? And that's exactly what we do in the Respire protocol. So in Respire, there's 2 parameters of interest. There's D, which is the ring dimension. This is the dimension of the vector that I'm encrypting. And then there's H, which is how many elements do I actually care about, right? If H is much, much smaller than D, we can actually get savings. And the idea is as follows. Let's say H equals 4 and D equals 8. So I only care about 4 things, but I have to encode everything using a vector of dimension 8 because that's what the scheme gives me. What I can do is I can just encode the part I care about, and I'm basically just going to truncate the ciphertext polynomial, right? The ciphertext polynomial will have 8 components in it. If I encrypt anything, whether it has zeros or ones, doesn't matter. The ciphertext is agnostic to that. It has to be, right? It can't leak information about the message. But what I'm going to do is I'm just going to truncate it. I'm going to not give you the full components of the ciphertext. And now this could be a problem for correctness. It's like, I'm only giving you half the ciphertext. Can you still operate on it? So it turns out that the answer is yes. There's actually some robustness in how the ciphertext encoding works, where we can actually develop an efficient decoding procedure that takes a truncated ciphertext and expands it into a full ciphertext that has zeros in all of the subsequent components. I won't have time to go into the details of how this is done, but if you look at the algebraic structure of the regF encryption scheme, you actually get this kind of property, that if you truncate the ciphertext, basically what that does is it replaces the truncated pieces with garbage, right? So the parts that I'm not looking at, because I don't give them to you, basically that's as if I communicated random values in those slots. And it turns out that there's an algorithm that we can use to actually zero out all the slots that we don't use. So we just have that server do the zeroing out, and then we are back to where we started. So yeah, and the way we do that is we use these homomorphic automorphisms. So these Galois automorphisms that modern FHE schemes all support. Okay, so that's how we compress the query, right? We just truncate, drop everything that we don't care about, and have the server sort of fill in the gaps as it does the computation. So what about the responses, right? So here again, normally in a response, we would have to communicate a full ciphertext. But what if the response is much, much smaller than a single LWE ciphertext, right? If the response is, let's say, if I have 2048 components in my ciphertext, but let's say the response only needs 2 components, do I have to communicate the entire ciphertext? And the answer again is no. Basically, if the record is much smaller, we can use another algebraic transformation. This is something called ring switching that was actually very old, came from the early days of FHE, which basically says that if I have a ciphertext defined over a large space, I can actually translate that into a ciphertext over a small space, a ciphertext namely over a subring. And that's basically what we do. The caveat is that once we project into the subring, we cannot do many homomorphic operations anymore, right? So you can ask, why not just use a small ring to begin with? We cannot do enough homomorphism. In order to do enough homomorphism, we need to work over the big ring. But the point is that once we are done doing the computation, once we don't care about doing more computation, we can sort of compress. We can project down into the smaller ring. And that's what we do here. So this is a way to get response compression. And so if you combine these 2 pieces together, you can actually get construction where both the query size and the response size are both actually much smaller than a single ciphertext. You can actually compress both. Okay.
So one question. So by basically applying ring switching, what you're basically saying is my new ratio in a ciphertext of useful information and potential error, it already starts at like 50-50 or 49-51, let's say. So like exactly. the minimal such that you can now recover, but if you do one extra operation, everything is noise and there's no going back.
That's exactly. Yep.
Okay.
Yep. And the point where I cannot do any more operations. So, but I'm done at this point. I already have the answer, so I just need to compress. Exactly
okay. Thank you.
Just distilling the long ciphertext into only the part that contains the part I care about. Okay, good. So just to summarize, I want to say a little bit about some of the more recent developments and also in PIR. So this is mostly not my work, but I just want to give you a sense for what's going on in the field. So I mentioned at the very beginning the simple PIR protocol where the client downloads a large hint at the beginning. So the simple PIR and its extension double PIR has the property that it's very high throughput. Basically, the server processes the database at basically the speed at which it can read the database into memory. This is very good for databases with very small records because the rate is very poor. So for every single bit of the database, you might have to download a few hundred kilobytes. So if you have a very large records, this is going to add up very quickly. But if you have very small records, this is actually extremely fast and extremely simple. So it's a very nice protocol. One of the drawbacks is it has a very large hint. So a hint for a reasonable sized database might be something like hundreds of megabytes, few hundred megabytes that you have to download. This is also a little bit tricky if the database is constantly updating. So for applications like certificate transparency, when a database is constantly updating, it means that every time the database updates, you need to download an updated hint. The updated hint can be very large as well. So there's a lot of maintenance involved in this particular type of construction.
Do hints, sorry, David, do hints have any kind of like incremental property, meaning you can profit from previous hint to already, let's say,
they're updatable. So if I only change a few rows of the database, then only a few bits of the hint actually has to change.
Okay.
Yeah. The only issue is that for applications like certificate transparency, usually what happens is I have a Bloom filter. So the database is actually a Bloom filter of all of the issued certificates. There's like every time a small number, even though I only add a small number of things to it, many rows of the database actually changes. And then you end up having to download the hint every time.
That makes sense.
Yeah. So depending on the application, it may be the maintenance could be more difficult than otherwise. But yeah, for some applications, if this database is mostly static or has only local changes, then this is perfectly reasonable. Right. So a question then is, can we get rid of the hint? So this was a recent line of work from last year. So by some folks at Google, the hintless PIR, and then my work with Samir on YPIR, we basically show how to remove the hint from simple PIR. Again, using sort of the same kind of lattice machinery that I described in this talk, using homomorphic encryption and composition. We can get comparable throughput, so essentially memory bandwidth throughput, at the cost of slightly more communication. So we don't have the hint anymore, so that as a result, each of the individual queries are slightly larger. Not by too much, maybe a few hundred kilobytes, but slightly larger, but no hint whatsoever. This is very well suited for a dynamic databases because there's no maintenance involved here. And then there's also this another line of work by Piano, so this is by Elaine Shi and her students, where they actually explore this fascinating domain where the throughput on a server can be very high. And this is very important if we want to scale to databases that are significantly larger. So right now, all of the schemes I described in this talk and all of the schemes described up here, the server has to do a linear scan over the entire database. So a linear scan will become too expensive if, let's say, the database is 100 gigabytes. Let's say you can read memory at a rate of 10 gigabytes per second. It's going to take 10 seconds to just read the database. So when a database is big enough, existing constructions are not going to cut it anymore. We really need something that has a sublinear server computational cost. So Piano is an example of such a construction. It has a sublinear server computational cost. So in fact, the server cost is roughly square root of the database size. So this is amazing from a throughput perspective. It does have a the limiting factor though, is that it also needs a pre-processing step. And unfortunately, the pre-processing step is extremely costly. It requires the client to basically download the entire database once. The client doesn't have to store the database. So this is almost like the trivial PIR construction where you're downloading the database once. You don't have to store it, but you do have to be able to download it. So sort of it's the parameter regimes where this is very interesting is the case of large databases, but then the fact that you have to download 100 gigabytes of database makes it very difficult to deploy from that perspective. But I think it offers a very interesting new point in this trade-off curve that I can trade off offline communication for online throughput. So I think it's very interesting to explore this further as well.
I have one question in regards of that, which is, we've been also considering the fact of performing like packetting in order to have a search that is not linear. Of course, that incurs into issues with privacy because you are leaking which buckets you need to go And so if you do that, then you can kind of track things somehow. Let's say you are revealing a lot more than you were previously.
Right.
So how does this play with things like ORAM, for example, where it can maybe serve as this, I don't know, alternative to the linear scan? Or maybe it's not, the state of the art is not good enough, but I don't know.
Yeah, so the tricky part with ORAM is that it's single client, single server usually. So it's not clear how to actually use ORAM to support a lot of these applications, just because for ORAM, you need per client state. And basically, the client and the server have to have a lot of shared state in order for our ORAM protocol to work. So every single client that joins the system will need to have different state on the server. And essentially, you need like a different replica of the database, sort of this ORAM data structure for every single client. So at scale, it's not clear to me that that ORAM would be effective just because there's so much per client storage that you need. Versus with PIR, you just need one copy of the database. You don't need to pre-process the database differently for every single client. So that's sort of the main difference between the two. Now, of course, ORAM does give you very nice other properties. It gives you stronger privacy guarantees, and it can also do some of these things in a sublinear manner. But I don't think it's a protocol that works with, let's say, millions of clients all querying a single server.
So do you foresee any let's say, technology or alternative that allows skipping the linear scan, which of course doesn't require the client otherwise?
Currently, no. Right now, I think schemes like Piano and sort of the follow-ups are the best concretely efficient mechanisms that skip the linear scan. But there's some actually very interesting theoretical work, sort of this notion of doubly efficient PIR, where there is no pre-processing whatsoever. It's a silent setup, just like hintless PIR and YPIR, where the server does a one-time encoding of the database, and then it answers all of the queries in sublinear time. So this, I think, is an amazing development in a sense that it gets around this. The server computational cost is much smaller. This is quite amazing. The communication is very small. The only problem is right now is that this is a purely theoretical construction. But the fact that we have a theoretical construction shows that this is a feasible notion, right? And we don't have a practical way of realizing it today. But the hope is that maybe 5 years, 10 years down the road, we can actually see this working at scale. So right now we're very far from that. But the fact that something like this is even feasible and that we can do it actually gives us hope that this linear scan barrier is actually not so significant, that potentially there are ways around it. Now, certainly today we don't have good ways of getting around it, but for upcoming in the future, I think there is a potential that something like this could be doable.
Makes sense. Thank you.
Yeah, so just to sort of wrap up, there's a lot of other directions that people have been exploring for PIR. So looking at handling batch queries, supporting keyword query search, doing some kind of authentication. So there's a lot of other ways that we can augment basic private information retrieval protocols to have stronger and better efficiency and security requirements. And these could be useful for different applications. So I think it's a very exciting time to work in PIR. There's a lot of very recent developments. The field is constantly evolving, and we made a lot of great strides in bringing this stuff closer to practice. We're starting to see deployments of this. So I think there's a lot of interesting opportunities to explore in this space. So with that, I'll conclude. I basically told you about the Spiral and Respire, which is one sort of data point in this very crowded space now. This is basically the approach if we want to take to get very communication efficient constructions. I didn't have a chance to tell you about how to get the high throughput constructions, but hopefully this still gives you a sense for one particular paradigm for realizing private information retrieval. So thanks, and I'm happy to take any further questions now.
Thank you very much, David. That was really nice. I think Yanis had a question, or
Yes, thank you, David, for your presentation. It was super compelling. I do have a question around like the security assumption and the privacy assumption of the scheme. Like one intuition that I have is that as soon as I send like my encrypted bit vector and we do the scalar multiplication to select the layer that we need to, like the intuition that I have, I'm not an expert in hardware. I know very few of it, but just my intuition is that like there might be like some side channel attacks, like where Because I guess that the CPU is doing less work when it's multiplying by 0 than 1. I don't know.
No, so because it's multiplying by ciphertexts, you actually can't tell whether it's an encryption of 0 or encryption of 1. So they actually look the same. So if you look at the amount of work that the CPU does, it actually does not depend on a query.
Okay, and that's the linear property of the scheme.
Yes, exactly. So because I touch every element in the database, and the amount of work I do for each element is exactly the same, you actually don't learn any information.
Okay, nice. Thank you very much. And also, I do have a question about like the setup of the database. How is it proceed? Like what's let's say that I want to set up my encrypted database. Is there any like specific setup about like processing it?
Yeah, there's some pre-processing. So you do want to encode the database using these lattice-based encoding schemes beforehand, but it's sort of a one-time cost. So it's like once I tell you the database, so I have a list of records and together with the index, basically you do a pre-processing operation on each of the individual records.
Okay, nice. Thank you.
Yep.
I have another question. So today's 29th. So yesterday there was a new paper called Distributional Private Information Retrieval from the MIT people. And this kind of seems to maybe breached into like, I don't know if it's directly, I haven't read it, but is it directly related to not needing this linear scan directly based on
a linear scan because they're building off of simple PIR. So I'm not sure they get around the linear scan, but I think they have other optimizations that actually allow you to further improve the throughput and reduce the communication. So I don't know the full details yet, but it's sort of a variant of simple PIR for settings where you sort of relax the correctness requirement. So I think what happens there is that for most queries, for the most common queries, is very close to being correct. For sort of rarer queries, there may be some small probability of error. And because you allow for this small probability of error, you can actually get away with much better performance.
Yeah, when I saw it, I thought it fitted pretty well with one demo that your co-author built, which was private Wikipedia article.
Right. I was going to show the demo, but I think
indeed, I think that's the case. It's just in Wikipedia, there's pages that a lot of people look for, and there's others that probably no one takes a look in a lot of time. So maybe a scheme like that could be like a way to enable people to try to see if they are lucky, let's say, and they can get this query privately, and otherwise they go back and rely on the normal, let's say.
Right, exactly. Yeah, so I think something like that could be quite interesting. Like a demo like that really showcase this type of system. Right, but yeah, I think a lot of these constructions are at the point where they are efficient enough to handle reasonable workloads. Not every workload is possible. But for many simple applications, I think the performance that we currently have, both in terms of compute and in terms of communication, are actually at a level where they can actually give privacy-preserving solutions to some of these challenges that are out there today.
Thank you. Thank you very much, David. I think there are no more questions. I will just send you in the chat the paper of Newton PIR.
Okay, sure. I'm happy to take a look, and I can follow up with you about it offline.
And I will post